In this video, I'm going to discuss quantum entanglement. And so I go into a lot more of the detail, especially with the mathematics for this in my quantum mechanics playlist, but we will touch on the sort of conceptual part of it in this video. And so entanglement is when two or more particles have correlated states, such as spin. But this could be any of the quantum states that we are interested in, like location and momentum and energy and things like that. So the spin is, so if we look at spin, it's a sort of intrinsic angular momentum within a particle, but it doesn't have a good analog in classical physics, meaning that nothing is spinning around an axis of any kind. But the reason it's called spin is because it makes the particles behave sort of like they are spinning. So they behave in a similar way to a spinning object. And so if we think about if you've ever played ping pong or table tennis or whatever you want to call it, you can sort of move your paddle as you hit the ball and give it some spin that causes it to veer in one direction or the other. So if you pull your paddle sort of inward like this, it'll cause the ball to sort of curve outward like that. And similarly, if you pull your paddle in this way while you hit it, it causes it to curve sort of outward like that. And so you can get these curving paths for the ping pong ball when you put spin on it. And so we get the same sort of curving path observed when we look at spin. So for instance, in the Stern-Gerlach experiment, where we send these, I think they're silver atoms, but you could think of them as electrons as well if you want, because it's the spin of the electron that we're actually looking at. And so you send it through an inhomogeneous magnetic field here, and there's a 50% probability that the particle will sort of veer up as if it's spinning, or veer down as if it's spinning in the other direction. And so that's why they call it spin, is because it when you put it through this magnetic field, it's almost like it's putting a spin on it and causing it to veer in one direction or the other. So formally, we can put it this way. So we have some spin operator acting on our wave function, and that gives us the eigenvalue of the wave function. So this lambda is the eigenvalue, and the psi is the eigenstate or eigenvector. And so this sigma right here is going to be one of these three sigmas here, which are called the Pauli matrices. And so this the x direction one is this one where it has ones in the off diagonals. The y one has the imaginary number I in the off diagonals, and then the z one is just sort of the well, it looks kind of like the identity matrix, but we are acting on a set of eigenstates, and these would actually be what are called the spinors. But I won't get into that here, but these are eigenstates, and so we have the plus z direction. So we're thinking of this in the z coordinate system. So we're always measuring things in the z axis here, and so the plus z would be this 1 0, and then the negative z would be this 0 1. And so we can say that we have these two eigenvalues here acting as the components in this, and so we get this as our state, such that these are normalized to have the square of them added to equal to 1. And so because they're a probability, well, when they're squared, they are a probability, and so the probability always has to come out equal to 1. So for this discussion, we will concern ourselves just with the xz plane. And so we can think of the particles, if we're looking at it like this, as sort of moving in the y direction, so sort of moving into my screen here. So the spin will be measured sort of up, down, and left, right, where z here is in the up, down, and x is in the left, right. And then we can have some n hat here, which is just sort of an arbitrary angle here, so we can have some angle theta here. And so when we are in between one of these, then we have to use this n hat here. So then we have so this would be the basis for the x direction if we were to measure these in the x direction. So what I showed up here with the 1, 0 and the 0, 1 is the z basis up there. These would be the x basis. So if we measure some arbitrary direction n hat, that forms an angle theta with the z axis. So remember, we're forming this angle with the z axis because we're always use, well, not always, but we're often using the z basis here. Then we get this. So we have this n dot with the sigma here, and so that's sine theta times the z direction Pauli matrix plus cosine times the x direction Pauli matrix. And so we get this rotation matrix here. So then the eigenvectors of that would be these right here. So for instance, if we have a particle with a spin prepared in an angle theta equals 60 degrees, so this angle right here being 60 degrees off from the z, then the eigenstate, so we have this theta over 2 in our cosine and sine here. So we put 60 divided by 2, so that's cosine and sine of 30. And so cosine of 30 times this plus sine of 30 times this. And so when we sort of put that together, what we end up with is well, we're looking at just this one because we want the probability of the negative z direction. And so that would actually be a 25% chance. And so if we are sort of at a 60-degree angle, which would probably be kind of closer to right here, it's saying that there is a 75% chance that when you measure it in sort of the up-down z direction, that you will get, there is a 75% chance of getting spin up and a 25% chance of getting spin down from that. So if we have an n particles, if we have a system of n particles instead of just a single particle, then this obeys the n particle Schrodinger equation. So what this means is that there is not a different wave function for each particle, but there is a shared wave function for all of the particles in the system. And so in general, that would look like this. But if we want to limit ourselves to a two-particle system, it will look like this right here, where these are the linear combination of the first and second particle here, and then the potentials for that there. And so we can have our V be an infinite potential well of length L, and so that will look something like this, where from 0 to L, the potential is 0, and then everywhere else it is infinity. And that will give us a solution that looks like this. So in the 1D solution to the Schrodinger equation, so that is this particle times this particle, and so it's this wave function times this wave function, and this is just the time dependence right here. But in fact, a perfectly valid solution would actually be to sort of change the other direction. So this one now goes to here, and this one goes to here. And so we see that this n and this n have changed places. This m and this m have changed places. And so actually what we see is that a linear combination of these two is a valid solution. And so we have it in this order plus having it in this order, because these can be in either order there. And so if we look at this in configuration space, so when we are looking at the x2 here, we see we have a sort of sine wave that looks like that going that way, and then this one is just a wave that looks like that, where here we have the sine wave looking like that, and then the sine wave looking like that for the particle 2. And so each of these is a valid solution here in configuration space. So here on the left, we have the configuration space for this. where for the x1 we see that we have just the 1 right there, and for x2 we have the 2 right there. And so we're thinking about it this way, where this is the sort of single hump here, and then this is the double hump where one is in the positive direction, the other negative. And so this is the one for if the second particle is in the excited state and the first particle is in the ground state, where this one is with the second particle in the ground state, and this the first particle is in the excited state. So what this means is that particle 1 is in a superposition of the ground state and the first excited state, and particle 2 is in a superposition of the first excited state and the ground state. And so what this means in practice is that there is no way to distinguish which particle is in which state. They're both sort of in a superposition of both states. And nor can we say that either of them is definitely in one state or the other. So if we sort of added these two things together here, we see that this and this part would constructively interfere. This part and this part would constructively interfere. This part destructively, this part and this part destructively. And so we end up with a state space that looks like this, which tells us that it's extremely likely that upon taking the square or multiplying by the complex conjugate, either both particles will be found on the right side of the well, so that would be sort of right here, or that both particles will be found on the left side of the well, so near 0 right there. So the particles, in other words, are entangled. This also works for spin as well. So we have spin that looks like this, and this would be the singlet state here, which means we have the negative sign right there. But what's important is that we have the first particle spin up, second spin down, or we can have the first particle spin down and second spin up. So they are correlated, or I guess what you might call anti-correlated. Which tells us that if particle 1 is measured as spin up along z, then particle 2 will be measured as spin down along z, and vice versa. And so this actually works at any distance, and so this is kind of the thing that really irked Einstein here, is that there's no time dependence on this. It works instantaneously. And so, for instance, if we have Alice and Bob both take one particle in a pair of entangled particles, and Alice makes her way to the Andromeda galaxy while Bob stays here in the Milky Way, and then measures her particle as spin up along z, she will instantaneously know that Bob's particle would be then spin down along z, because they will have that anti-correlation there. But yeah, that is sort of the concept here of entanglement. So you can kind of think about it. You have your two particles here, and one is way over here. As soon as you measure this one, without this one even having to like send a signal over to this one already sort of takes on a state. So you measure this one as spin up. This one then will definitely be spin down at any distance and instantaneously. And so that is, like I said, kind of the thing that Einstein was really worried about. And so we will actually discuss that in future videos when we talk about the EPR paradox, and then when we talk about Bell's inequality and things like that. But anyway, I hope you found this video interesting, and I will see you in the next one.